Hello, Chemistry 30, and welcome to your question and answer video for March 30th. We're going to go through the questions that you submitted on the Google Forms weekly check-in sheet, and I'll answer your questions as best as I can here in this format. Just a reminder that if you are still having issues, if you want some one-on-one help, I am on Zoom from 1 to 2 on Monday and Wednesday for your class. So feel free to drop in, right? Just kind of ask a question. I'll try to show you some stuff on whiteboard. You don't even have to turn on your webcam or your sound. You can literally just actually talk at me through the chat, and that's fine. I will answer and do my best to help you out. Okay, so here are the questions that came up that kind of I thought were good to show you. Some questions were like kind of duplicates or had the same themes. So I tried to just like pick the first one that I got that had a certain theme, and then if I saw a duplicate of that was similar, then I left it off of here. But some of you might look at this and be like, oh, hey, that was my question. Yes, it was. This came directly from responses from the what are you confused with question, what can I help with, that sort of thing. Okay, so the first question that came up is just confusion about differentiating between oxidation and reduction, but I believe it will come with more practice. It will, but this is definitely the backbone of the whole next two chapters. When I go through this in my mind, it's not completely simple. I actually have to think through it as well and think, okay, Leo the lion says grr, so loss of electrons means oxidation, right? So again, this is loss of electrons, and reduction is gain of electrons. Now, that's only part of the story, because then you have to think about, well, what does that look like in terms of what's happening to the chemical, and then also what does that look like as a chemical reaction? Well, when I look at a half reaction, if I have oxidation, that means electrons is a product. Because it's being lost, I'm losing electrons. So electrons have to be produced or lost from the original chemical right here. Well, for reduction, how this will look instead is that electrons will actually be gained. So electrons will be a reactant. So here, this is a reactant. And then when I have oxidation, electrons are a product. The other kind of simpler way to remember this is what I keep on saying in the videos, and I sound ridiculous when I say it, but when I go ner, right, what I'm saying there is that if it's becoming more negative, it's reduced. So for example, if Cl2 gas ends up becoming 2 chlorides, 2Cl minus aqueous, this became more negative. So if it became more negative, that's reduction. If I have something that becomes more positive, like zinc, Zn2 positive turns to Zn, oh, nope, that's reduction. I just did the reverse of what I wanted to do. If I had, Zn solid turning into Zn2 positive aqueous, this became more positive. It started out with a charge of 0. Now it has a charge of 2 positive. So it became more positive. So that's where I say poo, as in positive oxidation, PO, right? If it's becoming more positive, it's being oxidized. Oxidation is taking place. And then this brings us to the agents, which is the second question, the differences between oxidation reduction relating to the oxidizing agent and the reducing agent. So here's the thing, the OA and the RA, these are the chemicals, okay? That's the chemicals that I'm talking about. So kind of like I said in the video, it's like the noun. Well, oxidation and reduction are like the verbs. So the OA is always going to get reduced, which means that it is gaining electrons. Well, the RA, is always oxidized, which means it is losing electrons. So what is always happening is that electrons are going from the RA to the OA. In the process of electrons going from the RA as it oxidizes and loses electrons to the OA as it reduced and gains electrons, that's the basis for our redox reactions. The fact that one thing is losing while the other thing is gaining. Okay, that's what redox is. That's what we're dealing with. Essentially, what we're doing in this whole chapter is we're looking at a certain subset of reactions in a different way. We're learning a new tool to study them, and we're studying them in the context of electrons lost and gained by looking at the transfer of electrons between two things, between the Ra and the Oa. That's exactly what we're doing in this whole chapter, is looking at reactions in a new light of electron transfer. And then by looking at electron transfer, in the next chapter, we get to learn about applications of this. So things like batteries, right? Electroplating. That's the next step, is now that we know that electrons are moving in these reactions and we can study that, now we can actually apply it to stuff and we can go further with that. Okay, the original half reactions and just in general how all the topics relate to one another. I feel like I maybe just answered that. I'll go through kind of again the idea, not the half reactions part, but how the topics relate to each other. What we're doing is we're studying electron transfer in reactions. Not every reaction involves electron transfer. That's actually a later lesson that we'll go through. Specifically, double replacement reactions, no electrons are transferred. But for many reactions like combustion, photosynthesis, cellular respiration, single replacement, decomposition, formation. Electrons are transferred in all of those, so I can use the electron transfer to actually study these reactions again in a different light. That becomes very useful. And this will become more clear, I think, as more lessons happen and as you go through more material. The original half reactions, and then this kind of fit in, so I put this question as well. Can't figure out the electrons with half reactions. Great, let's go through, a few examples. So let's actually just start out with something really simple, like, well, let's go with chlorine is reduced. So if I'm looking at the reduction of chlorine, I would start out with chlorine as Cl2 gas. And then what that's going to make, right, because the only thing that can happen to chlorine, if it's just chlorine, is that it would turn into its ion, which is a negative anion. So I would end up getting Cl minus aqueous. And by the way, almost everything except for elements is aqueous in this chapter. That's a later question that we'll talk about. That actually the lesson for tomorrow, we'll talk more about states and then that'll probably clear it up. But yeah, almost everything is aqueous. Anyways, I have Cl2 gas and I have Cl minus. I need two of these to make that happen. So now, where do the electrons go? The electrons go on the more positive side. So right now, I have on the left-hand side a charge of 0, and on the right-hand side, I have a charge of -2. So electrons will always go on the side that is more positive because electrons are negative. So that will then allow me to make both sides equal if I add the negative thing to the more positive side. The goal is always to make the charge of the left equal to the total charge on the right. That's always what we're doing by adding the electrons at the end, is by making the total charge equal between reactants and products. So in this above reaction, I have 0 on the left, I have 2 negative on the right. I need to add 2 electrons to the left in order to make the charge equal on both left and right, to make it 2 negative for both. Right? And again, it's because I have 2 negative here, so I have to add electrons to the more positive side, which is here, until I can make that happen. If we want to try another one, right? Let's say that we had something like copper 2. I'm not loving that example. Let's go ahead with something just, whoa, that was fun. That was fun what just happened there. Let's go with something like Zn2 positive aqueous gets reduced. So zinc ion, my technology is making me struggle here, gets reduced. So zinc ion is turning into zinc, right? So I would start out with my Zn2 positive aqueous. That would be my first reactant. And I'm making Zn solid. Okay, now how do I know that? That's the only thing that can happen to zinc, right? It's not multivalent. It only has one charge. So the only thing that can happen to the zinc ion is it can then get changed back into zinc. So if I have Zn2 positive and I have Zn, then I have a total charge of 2 positive on the left, I have a total charge of 0 on the right. So what do? Well, I add 2 electrons to the more positive side. So I'm going to add 2 electrons right here, which will now make both sides equal at a total charge of 0. So what you do with electrons, add them to the more positive side. Okay, that would be the direction I have for you. Okay, so that's that set of questions. Moving on, complex half reactions. Yeah, they're tough. They're tough. So as I said in the video, you're always kind of going through the same 3 steps. So first of all, you are going to balance the other stuff. Okay, so balance atoms that aren't H and O. Okay, leave the hoe for last. For 2, we're going to balance O, so balance oxygens with waters, okay, H2Os. And then I'm going to balance H's with H positive. And then finally, I don't know why I put a G there. Geez, it is Monday. Aqueous. And then finally, I'm going to add electrons to more positive side. And that is to make the charge equal, right? Like we talked about in the last question. So I'm going to add it to the more positive side to make it equal. Now, why can I use H positive? I can use H positive when it says something about it being acidic. Okay, so if I have an acidic medium, I have H positive at my exposure. How do I know I have water? I always have water. It's always in there. I have tons of aqueous stuff. These reactions are almost always happening in solution. So because of that, I pretty much always have water available. So I can add water to either side because it could be a reactant or a product in my mix. Okay. So here's a couple of examples. I thought it would be useful to go through some live with you if this was a problem. So here's question 7 and 8 from the worksheet. You have the key, yes, so you probably saw what the right answer is, but let's talk about the process. So I would start out by writing out what I know from the question. I didn't include that as a step earlier because I mean you just are writing out exactly what you have. So manganese 2 ion is Mn2 positive aqueous, and manganese 4 oxide, this is a weird one. This is MnO2 solid. I had a question earlier about how do I know that's a solid? Well, it isn't on your solubility table. Oxide isn't even on there. And in fact, almost every oxide is insoluble in solution. Almost everything else is going to be aqueous in this chapter, but MnO2 is a weird kind of thing that pops up a lot that is a solid. The only oxides that are soluble are ammonium oxide and group 1 oxides like sodium or lithium oxide. Everything else does not dissolve. And again, how do you know that? From checking your solubility table. So it's MnO2 solid. Okay, so we start out with this. I take a look now and balance my non-HO stuff, which is just the manganese. I have 1 and 1. Hooray, that's done. So now let's move on to the oxygens. I have 2 O's here. So I need to get 2 O's on the left. So to do that, I'll add 2 waters, and I'll add it on this side of manganese 2 for right now. So 2H2O liquid. Okay, so now I have my O's balanced, but now my H's are screwed up. Yeah, because I have 4 H's on the left, I have none on the right. So this is where I'll add 4 H positive aqueous on the right-hand side in order to make that equal out. And I can do that because it says acidic medium, so I have H positive at my disposal. Finally, the next question would be, how can I make the charge equal? So on the left, I have 2 positive for an overall charge, right? Because I have the 2 positive manganese. And over here, I have 4 positive. So that means that I can add 2 electrons to the right, and then that will change this to be 2 positive. And now it's equal. So that is a balanced complex half reaction. It's completed. So let's try one more together. Nitric acid reacts to form nitrogen dioxide gas. This could be a thing of where you actually pause a video, try it first, even though I know you did in the workbook. Hey, it's good a review to try it again and then come back to it. But here's the answer. So nitric acid, I have HNO3 aqueous, reacts to form nitrogen dioxide gas, so I have NO2 gas. So now I have one N, one N. So for my non-HO atoms, they're balanced. It's all good. Now I take a look at my O's. I have 3 O's here. I have 2 O's here. So I need to add a water to the right to get another O. So now I'm at 3 and 3. I now have 2 H's here, 1 H here. So I actually need an H positive on the left in order to make H equal. And now I'll look at my overall charge. I have 1 positive on the left, 0 on the right. So I just actually need 1 electron to make this work and make the charge equal out at 0. And I'm finished. Now, spoiler for later, you're actually going to be doing a very similar process with net reactions in the future, where you'll go through and add waters to make O's equal and then H positives to make hydrogens equal. So this isn't going away. We're actually going to be adding to it later on. Okay, I am confused about what disproportionation is. Other than that, I feel pretty good. All right, so disproportionation is when the same thing is both the OA and the RA. A lot of the problem with confusion around stuff right now is that you haven't learned the most powerful tool for redox chemistry, which is oxidation numbers, which will allow us to kind of revisit some things and understand some things a lot better. Right now, it kind of seems like, oh, you just assign numbers in terms of charges to stuff like magic. What I'm actually doing is oxidation numbers, but right now we're just saying, hey, it's ion charge. But we have to avoid a lot of examples because of that. But anyways, I digress. Disproportionation is when the OA is the same chemical as the RA, right? So a great example is if I actually had 2 copper 1 ions, so 2 CuO positive aqueous, which reacted to make solid copper, and then also to make a copper 2 positive aqueous ion. So this is a net reaction, but what's happening here is that I actually have the reduction reduction of copper 1 ion, so plus an electron to make copper. So that's the reduction taking place. And then I also have the oxidation of the copper 1 ion, so Cu positive aqueous reacts to make copper 2 positive aqueous and an electron. So both the OA, right, because this is getting reduced, and the RA, because this is getting oxidized, is copper 1. So this is a disproportionation reaction. We're going to not leave that there. We're going to do more disproportionation stuff later on, where you'll see questions with disproportionation. So this isn't going away, but just by definition, this means the OA and RA are the same chemical. Would be the easiest way to put it. And in fact, I can get more specific than chemical and say reactant. Okay, same chemical species. How to determine states in redox reactions. So this will become more clear actually in a day once we talk about states and major entities and stuff. So essentially, what I can tell you right now is that all ionic compounds that are soluble turn aqueous. Okay, so soluble, turn aqueous. And when ionic compounds are soluble and they turn aqueous, they dissociate, which is something that you learned about in Chem 20, but that means that they split up into the 2 ions that they're made of. So for example, if I have something like calcium chloride, CaCl2 aqueous, that means that what I actually have in solution is Ca2 positive aqueous, and I have 2 chloride ions as well floating around. Right, so I actually have these ions in solution. It's not staying together as a compound, but it splits up into ions dissolved as an aqueous solution. So all ions that we're using in redox reactions are going to be aqueous, okay? All the ions are aqueous. All the elements, you're checking the periodic table, right? So this is the original state from the periodic table that you're dealing with. Besides that, just take a look at your solubility table for anything ionic, see if it dissolves. For acids, you'll learn this again, like I said, tomorrow. but strong acids, they turn into H positive in the anion. Weak acids stay intact, but they stay aqueous. Okay, disproportionation we already talked about. In acidic solutions, is a reactant compound, a product compound, aqueous unless specified, told otherwise. So I feel like we just talked about that as well. Yeah, so pretty much like all ions are aqueous, right? In redox, that's what we're dealing with, is all ions are aqueous because they are dissolved in solution and they've dissociated from the ionic compound, and so now they're free in solution as ions. So hopefully that clears it up. Okay, this is not actually about material, but about kind of how the course is going to be run. So how and when will we be doing quizzes or tests? You won't. You won't be doing quizzes or tests is really how it looks right now. I don't want to say that definitively because things could change, but I can't give you a quiz or a test without knowing whether it's secure or not, whether cheating is happening. It's not fair. Okay, so essentially, like, there's a really big problem with giving quizzes and exams that I don't feel like they're a very good assessment tool right now for me to tell where you're at. Now, you do have the quizzes online, but I'm giving you unlimited times to try that. It's about the feedback loop, yes, more than it is about like me collecting a mark. Your mark, or what I'm looking at right now for assessment to see how you're actually doing, will be your assignments. You will get your first assignment Wednesday, I think I have it set as on the weekly schedule. So that'll be the first time where it's like, hey, here it is. Here's an assignment that I'm going to mark, and I'll actually like full on go through the marking process, giving you check marks, X's, totals, all that jazz, and feedback so that you're learning from it. But that is the primary thing that will be determining your mark. Is it perfect? No, it's not perfect. This is not ideal. Yeah, I mean, this is not how normally a course would be delivered, but this is what I feel like is the best tool I got, is a worksheet where I can see the process and you're working through it. So what is your focus right now in Chemistry 30? Your focus is understanding of the material. We don't even know what final marks will look like in Chem 30. We have no idea. We don't know if it's even going to be just a pass or a fail or a pass with honors or something. We don't know if there will be percentages. We have no idea what the reporting aspect will look like. That will still be decided. The districts are talking to the education minister. There's a lot of back and forth. Okay, but for right now, what I'm trying to do is make sure that you understand the material. You're going to do your part as well in getting the feedback, making you understand it, because you're going to need this later on for most of you. Yeah, with whatever program you're planning on going into in post-secondary or whatever your future plans are, I assume you're taking Chemistry 30 for a reason, that you didn't just somehow, whoops, I'm in Chem 30. So given that, you are working on making sure you have good understanding of the material as you go through. This is a little bit of you being an independent learner, being honest with yourself of what you're struggling with, what you're not, and working at it. And I feel like I said this before, but man, is this great training for university. Because in university, you don't have a lot of feedback. You don't have a lot of hand-holding along the way. You have a midterm and a final that makes up almost your entire grade. And in the meantime, you have to make sure you have understanding of the material. You have to be independent. You have to be self-motivated. Okay, so this is a little bit of training of just making sure that you understand everything. Given that, I get it, there isn't a final exam that's slotted to keep you accountable. I'm trying to keep you accountable with the quizzes, with the feedback, with the assignments, but you have to also keep yourself accountable as well to make sure you have the learning. And wow, was that long-winded. So how and when will you be doing quizzes or tests? As of right now, I do not plan on doing any quizzes or tests besides the quizzes, yeah, that you're doing for feedback, okay, which is really mainly formative for you and for me. Okay, so those were the questions and answers from the last week. Maybe it gives you an idea too of what that check-in document purpose, what purpose it serves, and that it provides me with these questions, allows me to actually have a little bit of back and forth with you. But yeah, that's it. All right, well, you guys enjoy the rest of your day.